And welcome there, function folks. This is the lesson on instantaneous rate of change, and you know the routine. You've already tried the 3-minute review, and I'm hoping that you actually got stuck on the 3-minute review on this one right here. But we'll get to that after we take up the first couple. We were asked to calculate the average rate of change, where we're given a function that represents Ferd's distance from a certain point. We know the formula for Iroc now is this familiar formula, change in distance over change in time, or we like doing it d2, d at t2 subtract d at t1 over t2 subtract t1, this sort of deal. And here we've got t2 is 2 seconds and t1 is 1 second. So on the bottom it's easy, but we want to do some calculations maybe in the margin here. D at 2 is 105 times 2 subtract 10 times 2 squared. Bing, 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 and into the calculator goes, and that's 170. Similarly, when I take out t and put in 1, I get d at 1 is 95, and I calculate the average rate of change. No problem. And that's 75. What are the units? Well, distance is kilometers. The time was in hours, I believe. Yeah, hours. Kilometers per hour. What does your calculation represent? Between hour 1 and 2, Ferd was traveling at an average speed, average rate of change, average speed of 75 kilometers per hour. Okay, part C, this is the thing. How fast was Ferd driving at 1.5 hours? Was he traveling at 75 kilometers per hour? Not necessarily, because his distance was always changing, right? This is some sort of parabola. Opens down because, and between hours 1 and 2, we know he was 95 kilometers away and then 170 kilometers away. And we know average rate of change there was 75 kilometers per hour, but what was it at 1.4? We don't know, right? And we can't use our formula because we know one of these numbers should be 1.5, but how do we calculate the slope? We need another number. If this is T1, what's T2? Or if this is T2, what's T1? Right now, here we are stuck. And in fact, what we're after right there isn't an average rate of change, it's an instantaneous rate of change, which is what we're talking about today, which we're stuck on right now. And essentially, how we resolve this is we actually don't even calculate what the instantaneous rate of change is, but we estimate it. And that's what we're all about today, estimating rates of change. So recall, the average rate of change was the change in y over the change in x, right? The change in y over the change in x, where from P to Q, this was kind of the change in x, and this was the change in y here. And we also used the formula y2 minus y1, different color here, why not? Where this is x1, y1, this will be x2, y2, and we used change in y was y2 minus y1 over x2 minus x1, or even f at x2 minus f at x1. This was average rate of change. And where we got stuck was we didn't want necessarily the rate of change over an interval, but at a moment in time. So essentially at one point, say, what's the rate of change, the instantaneous rate of change at point Q? Well, you can guess, and I've got a demonstration of this. This is Geometry Sketchpad, something that I put together, that if I wanted to find the instantaneous rate of change, essentially what I need to do is I need to take this point P and drag it closer. So I need the run to get smaller and smaller. See, I need to get so small that it actually is in one instant. Notice right there, we're getting pretty close. The run is whatever, and the slope of the secant is whatever, and I can see my P and my Q are getting very, very close together. I want them to be right on top of each other, except for then I'd be dividing by 0. And I can't do that. So I've got to figure out how to calculate this with without actually getting right on top of it. And right there, let's see, I went away from right there, right? It's undefined. See, it disappears. But what I can do is I can sneak up and get really close. The slope of the secant here is 4.5, and as I move even closer, I can see the slope is going to be, well, it looks like it's going to be 4.5. When I have a run of 0.01, my slope is 4.5. For this one, it's not the same function, I realize, but that's going to be our strategy, is to calculate different p, take different p values, and then calculate the slope over smaller and smaller intervals and look for the trend. So let me just write that in your note. It's hard to do in a note to see P sort of drag closer to Q, but this is the thought. The idea is, as I drag P closer to Q, what happens? Then my rate of change gets closer to 0, and I'm going to get closer and closer to divide by 0. And what I end up getting closer and closer to is having this secant not be a secant anymore, but only intersecting the graph in one spot, what's called a tangent, right? A secant PQ gets closer and closer to a tangent at Q. And that's what we actually want to find. And in fact, this is how we're going to do it, because then the average rate of change approaches the instantaneous rate of change as delta x gets closer and closer to 0. And so there we go. The instantaneous rate of change, Iroc, instantaneous rate of change, is the rate of change of a function at a particular point. And like we mentioned before, it's the slope of a tangent. And we can't just put in x2 and x1 as the same point because we're dividing by 0. And we can't divide by 0, but geez, we're going to get pretty close. And here's how the calculation actually goes. Estimate the IROC of that at x equals 1. So the whole idea here is I've got a function. Let me draw a quick sketch of it. And this graph goes through 0 and also has another, it kind of looks like this, where I want to find the slope of that tangent right there. That's what I want, the slope of that tangent. That's the instantaneous rate of change. But I can't do that. I can't figure out what that is. But what I can do is I can take a value of P that's somewhere to the right here and then drag it closer. Now, what the heck do I mean by dragging it closer? Well, I'm going to pick P and calculate the average rate of change. And we're actually going to do this in 3 ways. So this first way is called a preceding technique. Preceding method. And the idea here is P is going to be to the left and sneak up on Q from the left. P approaches Q from the left. So what might I try? Well, here's my interval, and here's my Iroc. So if I try the interval from 0 to 1, so that means P has an x coordinate of 0, then I'd have my Iroc, y2 minus y1 over x2 minus x1 is going to be, well, I got to get out my calculator. Here, Q is the point 1, and then F at 1, 1 squared plus 2, that's 3. So Q is 1, 3, and P is going to be changing. So I'm actually not going to put P in here, because P is changing all the time. But in this case, it's 0 and F at 0, which is, well, 0. So I'm going to have 3 minus 0 over 1 minus 0. This Iroc is 3. So notice this isn't a very good estimate of the instantaneous rate of change, because P is pretty far away from Q, right? So my first average rate of change, my estimate for the Iroc is 3, but I know it's not very good because my delta x is 1 unit. It's not very good. So where would P be that would be closer? Well, I could move it a little closer, maybe move it halfway. So I'd have the interval 0.5 to 1. And notice 1 is the spot where we want to find our instantaneous rate of change. And then I go through the whole darn thing again. Here, F at 0.5, I'm going to have to get out my calculator. Right, and actually, I'm going to show you how you can sort of be faster at this, be smart with your calculator. This is a graphing calculator, obviously, but your scientific calculator should work the same way. 0.5 squared plus 2 times 0.5, and then I get my answer 1.25. Okay, dandy. So then I'm going to have Q is here, right? So 3 subtract 1.25 over 1 subtract 0.5, and that's, in my head or on my calculator, 1.75 over 0.5, which is 3.5. And notice that's a better estimate of my instantaneous rate of change, but still, certainly my delta x, my change in x, is still pretty big. So what would be even better than that? Well, let's sneak P up really close, maybe 0.9, and then my delta x is going to be pretty small, right? My delta x is 0.1, and so now I'm going to have my 3 subtract y1, and this is my p-value here, which I got to calculate. I know this is 0.9, and there's my, notice the 1 subtract 0.9 is that 0.1, that's my delta x. But I have to do this calculation again, right? And this is a pain. And that's why I wanted to show you on the calculator that most calculators, what you can do is call up the last entry, just go back, change the value, and that's faster. 2.61, which is going to be, again on my calculator, 3, and if I wanted to, 3 subtract 2.61 divided by 0.1, 3.9. You see a pattern here? 3, 3.5, 3.9. What's the slope of the tangent? What's the instantaneous rate of change going to be? Looks like it's getting closer and closer to 4, right? Okay, well let's just get a little bit sillier here. And notice When does this stop? Well, it's when we lose patience for getting closer, right? We could get closer and closer and closer and closer. This is now really, really close. Well, why didn't we skip to this straight off? Well, we wouldn't be able to see the pattern then, I don't think, especially for the very first one. And so now, you know what I'm going to do? I'm going to start doing this on my calculator, right? I'm not going to write in the entire calculation anymore. I'm going to start doing this on my calculator where I get 3. I'm going to put this in brackets. 3 subtract, and then I'm going to put this calculation in again. I got 0.99 squared. I need 2 brackets there, don't I? Right? Where I could have went back and I could have changed that, but I'm going to do it all in one step now. Plus 2 times 0.99 end bracket, and I'm dividing by my delta x, which is 0.01 this time. And where did I goof my calculation up? Oh, 2 times 0.99. Something wrong. Can you see my calculation error? 0.99 squared plus 2 times 0.99 end bracket. Don't know. Let me pause and I'll be... All right, I found my goof. You see, this bracket goes with this 0.999. This bracket ends this bracket, but I don't have a closing bracket for that. See, this is why I let you guys do all the calculations, and I usually just skip it. Let somebody else do the calculations because I am rotten on my calculator. And there you go. So maybe that would have been smarter if I did do that in 2 steps like I was doing before, but now it should be good. And I get my answer 3.99, which is closer to what I would expect. 3.99. And so, I mean, I guess I could stop, I could keep going and get closer and closer, but what does it look like? It appears that the Iroc at is about 4 units, right? That seems to be what the trend is. Now, this is actually just the tip of the iceberg, folks. So I'm going to come back and finish off this example. We'll get into example 2 because this is the preceding method. There's actually 2 more methods, believe it or not, and we'll get to that in part 2.